Hi again, CalBC. This is a quick video. I know that this is a lot of review for you guys. We're looking at volumes today. And so when we apply the integral as accumulator operation to a volume of a solid revolution or a volume by parallel cross sections. And so the idea is pretty simple. Find the area of the face multiplied by the incremental width, which is usually dx, and integrate that across your region. I won't spend a lot of time with you on it today, since I believe this is really something that we all hit pretty hard in Calc AB, but I do feel like I should review the two main methods for solids of revolution, and those are the washer method and the disk method. Sorry, the washer method and the shell method. There we go. And so we will take a look at those here today very quickly. So I'm just going to start with my sort of generic function, f of x, on an interval. And if this is what my function looks like from point A to B, and if I'm revolving this function around the x-axis, so we're going to go around this axis here, obviously we get, ooh, well, that's not quite right, but you get the idea. It's going to kind of do this thing where it's round, and this would be disks. And you know that if there's another function involved, if there was something inside like this, then we would have washers, because they'd have a hole in the middle. So the disk / washer method, depending, just a quick reminder. So you take one of those disks and or washers that we have, and you find the volume of it by taking the area of the face, which is just big circle minus little circle, multiplying by the incremental thickness, which is that dx, given the direction we're going right here. And so in the end, the volume, of course, the radius of the outer thing is the big R squared, right? That's big R of x. The radius of the inner, this one here, that's little r. And so, pi r squared is the area. So the pi doesn't need to be in the integral. And you have big R of x squared minus little r of x squared dx. And that's supposed to be an A down there. There we go. And there you go. That's your volume using the disk / washer method. If there's solid disks, then obviously little r is 0. So then it's just one radius function that you're worried about. And this, just as a quick kind of, rule, if your axis of revolution is a horizontal line, a horizontal axis, then usually the disk washer method is the way to go. It keeps everything with respect to x. When we did this last year, you might remember, both Mrs. Stuckey and I probably beat it into you that you want to shade in what we called the representative rectangle, right? There's a rectangle in there. And that rectangle is kind of how you orient yourself to your axis of revolution. Well, if the axis of revolution is horizontal, then having it be disk or washer method means the rectangle is perpendicular to the axis, and the width of that rectangle, that width there, is your dx. And that was the important thing when we were doing these, was to try and keep that width. Dx makes the integration, I don't know, for whatever reason we prefer dx, probably because that's what we started with. And there you go. So conversely, if the axis of revolution is a vertical axis, okay, then you probably would switch to the shell method, unless there was some reason why the shell method wouldn't work. And so when we have our function here, and we're going to revolve around, we're going to revolve this around the, let's just make it simple, from A to B here. And we're going around the y-axis now. Oh my. Like this. Boy, I'm so much better at drawing these on the board, guys. I'm so sorry. But you get the idea. There's a bowl kind of shape in the middle. Um, now what I would say is, yeah, I would probably switch over to the shell method. So, when we did the shell method, again, we still show that representative rectangle, in the region that you're graphed. But remember that when you revolve that around the axis now, it creates a thin cylindrical shell. So if I draw just an example of the thin cylindrical shell, um, it looks something like this. And let's go here to here. Oh, it's not quite straight. Well, we'll make it straight in a minute. There we go. And ta-da. And so the shell has that same idea that there's a thickness to it, right? And that's where your dx comes in, and you probably remember that from last year. So when I find the volume here, I'm still integrating from a to b. It's just now we use that 2 pi times the average radius function, rho of x, times the height. Okay, the average radius, remember, was from the center of the pipe out to halfway. So rho of x, the height, which is a function of x, okay, and then the width, which is dx. And so anytime the axis of revolution was a vertical line, finding rho of x was just simply how far over from the axis of revolution is that rectangle. And so rho was in a lot of them, if it's around the y-axis, it was easy. It was just, rho of x equals x. When they started moving the axis of revolution around, okay, so it wasn't the y-axis, wasn't the x-axis, okay, that's when you had to do a little bit more work to find those radius functions. But again, top function minus bottom function is always going to be a good way to do that, okay? Or right function minus left function is always going to be a good way to do that if you have to do vertical lines. So yeah, they're pretty straightforward. And like I said, we hit these pretty hard in Calc AB. I know we were in it was kind of during the shutdown for a lot of it, but we did hit these volume equations pretty hard. So anyway, just a quick reminder of how to do volume by the solids of revolution. The last one was just if the solid was formed by some sort of parallel cross section, there was we had the one. It's really going to be hard for me to draw this, but I will do my best here for you guys. Where we had the if this is the XY axis. Okay, so here's the x-axis, and here's the y-axis. And the region was some was like a circle in the XY plane. Tried to get that centered at the origin. I totally missed, so let's try that. There we go. Then our cross sections, were like squares or rectangles or triangles or whatever, and we said, oh yeah, so there's a let's just do a square that's perpendicular to the x-axis. So you had a square that was across like this, right? And then just bear with me, like that's actually a square. All right, and we had to find the volume that formed by those, and all we did really, guys, was just said, hey, well, look, we're going to treat it like it's a washer. We're going to find the area of this face, right, and multiply by the thickness down here, which is that's the dx, and so the area of the face, of course. Let me get a different color here. The area of that face is just side length squared. Well, the side length is from here to here. Well, if you remember the equation of the circle, then you know how to find that equation, the circle equation, x squared plus y squared equals r squared. And so then you just figure it out, right? Y is the square root of r squared minus x squared. And that's half the radius right there. So that's what we did. You probably remember that from last year as well. And then all you have to do is integrate it for the volume. I think you probably got a good lesson in use the symmetry of the circle last year, right? Because I could go from negative, this is negative r here all the way out to positive r, but y, it's perfectly symmetrical. Just go from 0 to r and double it, multiply by 2. So there you go. Side length is 2 times the square root of r squared minus x squared. Okay, square that, multiply by the width, dx, there you go, boom, parallel cross sections. And of course, they change the shape on you all the time. So just find the area. If it's a right triangle, use an equation to find the area of the right triangle. If it's an equilateral triangle, there's a nice equation for equilateral triangle area. If you've forgotten it, it's in the front cover of your textbook. So anyway, just a quick hitter video here on finding volume either by surface solids of revolution or by parallel cross section. So, all right, guys, thanks. We'll see you in class.